Dear friends, welcome to Digital Logic Design Sessions. In this video, we will discuss about SR Latch. The discussion will be done under three sections. In the first section, we'll look into the construction. In the second section, we will discuss about the working mechanism of SR Latch. In the third, we will see how to write the characteristic table and derive characteristic equation for an SR Latch. Let us start with the construction. An SR Latch can be constructed by cross-coupling two NAND or two NOR gates with the two inputs. So here in this picture, you can see the two NOR gates, gate number 1 and 2, are cross-coupled to construct an SR latch. So the meaning of cross-coupling is that output of one gate is fed as an input to the other. So here you can see the output of gate 2, that's Q bar, is being fed as an input to gate number 1. At the same time, you can see the output of gate number 1, that is Q, is being fed as an input to gate number 2. This way of connecting the output as an input is called as a cross-coupling. Now, look at the inputs. We can see that S and R are the direct inputs that are driving the gate 2 and 1 respectively. These are called as the primary inputs. Apart from this, we have the other inputs that are taken from the output of the other gates, right? Those are the feedback inputs, right? So Q and Q bar are forming the feedback inputs. Q and Q bar are not only forming the feedback inputs, they are also the outputs. So Q and Q bar have a dual role to play. They are feedback inputs or they are acting as inputs. Not only that, they are also the outputs. So they have a dual role to play. So this is about the structure and the construction of a SR latch. So here we need to take a look into an important condition. The condition is that Q and Q bar are considered to be complement of each other. It means that Q and Q bar are not allowed to take a same value. So if they are going to take a same value, then it's an invalid thing, right? Okay. So now, before we proceed to the working mechanism of SR latch, let us take a quick look into the two input NOR gate. What we have here, it's described by the truth table. So here is the truth table. So from this truth table, you can see that whenever any one of the input is 1, either A or B or both the inputs are 1, the output is 0, right? So from this, we can say that if any input is 1, you need not worry about the other input. The output of a NOR gate is going to be definitely 0. In case if the one of the input is 0, we must wait for the other input being defined. Then only we'll be able to define the output or guess the output. So this is an important basis which we need in order to understand the working mechanism of a SR latch, which is constructed using the NOR gates. Now let's move on to the working. The working we are going to discuss under 4 parts, and these 4 parts corresponds to the 4 binary combinations for the variable S and R, which are the binary variables driving our two NOR gates that are used to construct a SR latch. Every part we are going to discuss under 2 segments. So these segments corresponds to Q being 0 and Q being 1. Before we start analyzing and understanding the working of these segments with the 4 combinations, there's one more thing what we have to look in. So we are labeling the outputs as Q and Q plus. You can see Q and Q plus, Q bar and Q bar plus. Now the plus superscript has been used to discriminate this output which we are going to get after evaluating the NOR latch. So it means that Q and Q bar corresponds to the value that were existing before we applied the values for S and R. Okay, and Q plus Q bar plus corresponds to the value of Q and Q bar which we have found after evaluating by applying the value of S and R. So this value of Q plus and Q bar plus, we also call it as a next state, and the value of Q and Q bar, what we are going to consider before we apply S and R, we call that as a present state. So now let us start our discussion with the first part. So herein we are considering S equal to 0, R equal to 0. I will assume that Q is 0 in the first segment and Q bar is 1. So now let us apply S equal to 0 or equal to 0. Fine. So as we discussed earlier about the working of a NOR gate, if any one of the input is 0, we will not be able to say anything about the output until and unless we have information about the other input. Now here the other inputs are the feedback inputs, right? And the feedback inputs we have defined Q as 0 and Q bar as 1. Q is driving gate number 2. So gate number 2, both the inputs are 0 now. So the output Q bar plus will be 1. Now, one of the input to gate number 1, which is a feedback input Q bar plus, it's being 1. So the output Q plus will be 0. Okay. Now let's go for the second segment. Here in this, before I apply S equal to R equal to 0, I'm assuming that Q is 1. So Q bar is 0. Now I'll apply S and R as 0. So as we saw in the first segment discussion, so with S equal to 0, R equal to 0, we will not be able to define the output Q plus and Q bar plus until and unless we know the other inputs. Those are the feedback inputs. So Q being 1, so gate number 2, one of the input is 1, so Q bar plus will be 0. Now both the inputs to gate number 1 are 0, hence the output Q plus will be 1. So now in this part, what we observe is that when you apply S equal to 0, R equal to 0, output Q plus is going to be the same as the input Q. So if Q is 0, output Q plus will be 0. If Q is 1, output Q plus will be 1. So this is called as a latch state or memory state of the SR latch. Latch state or memory state. Okay, now let's move on to the second part. So in the second part, we are considering the combination S equal to 0 or equal to 1. Again, we are doing the discussion in two segments. So for the first segment, I'll consider Q to be 0, Q bar to be 1. Now with this, let us try to apply S0 or 1 and see what will be the output. Now, one of the input to gate number 1 is 1. So hence Q plus will be 0. And both the inputs to gate number 2 are 0. So Q bar plus will be 1. Okay, fine. Now let's move on to the second segment of this part. So I will consider Q to be 1 and Q bar to be 0. Let us apply R1 and S as 0. Now with R being 1, one of the input to gate number 1 is 1. So the Q plus is going to be 0. Both the inputs to gate number 2 are 0. That is Q plus and S being 0. So Q bar plus will be 1. Now in this part, what we observe with S equal to 0, R equal to 1. So irrespective of Q, Q plus will be 0. That is, if Q is 0, Q plus will be 0. If Q is 1, then also Q plus is 0. So this state, we call it as a reset state, wherein the output Q plus is going to be 0, independent of the last state, or I can say independent of the value what we assumed before applying S equal to 0, R equal to 1. So the output is 0. This we call it as a reset state. Okay, let's move on to the third part. So in this third part, we are considering S equal to 1, R equal to 0. Again, the two segment analysis. Let us consider that Q is 0, Q bar is 1. Now we are applying S as 1 and R as 0. So with S1, so one of the input to gate number 2 is 1, hence the output Q bar plus will be 0. Now both the inputs to gate number 1, that's Q bar plus and R being 0, the output Q plus will be 1. Okay. Fine, let's move on to the second segment. So I'll assume or I'll consider Q to be 1 and Q bar to be 0. Now S is 1, R is 0. Okay. So with the input for gate number 2, which is defined by S, is 1. So one of the input being 1, the output Q bar plus is 0. Now both the inputs to gate number 1 are 0, hence Q plus is 1. Now from these two segments, for this part, what we observe is that with S equal to 1, R equal to 0, irrespective of Q, whether Q is 0 or Q is 1, output Q plus is 1. So this we call it as a set state. We say that latch has entered into set state. Now let's go on to the fourth part. So again, the two segment analysis is with S equal to 1, R equal to 1. Now with S equal to 1, R equal to 1 in the first segment, I will assume or I'll consider Q to be 0, Q bar to be 1. Now I'll apply S as 1 and R as 1. No, one of the input to gate number 2 is 1. Hence the output Q bar plus is going to be 0. No, one of the input to gate number 1, which is R, is 1. So here the output Q plus is also 0. Now this is violating the condition what we have considered or what we have uh, uh, lay down in the beginning, that Q and Q bar should be complement of each other. So whereas here Q and Q bar are taking the same value. Okay, so this is violating that condition. Let's move to the second segment. Let's see what happens. I'll consider Q to be 1, Q bar to be 0. No, S and R both 1. No, what we observe is that one of the input to gate number 1, which is R, is 1. So Q plus is 0. One of the input to gate number 2, which is S, is 1. Q bar plus is 0. No, again, what we see is that Q and Q bar plus, that's Q plus and Q bar plus are taking the same value. So this is an invalid thing is as it is violating the condition Q and Q bar to be complementary of each other. So this state, we call it as an invalid state. And the corresponding input S equal to R equal to 1, we call that as an invalid input. So let's move on to the third section. So here in this section, we'll see how to write a characteristic table and derive a characteristic equation. So characteristic table we are going to write by listing the input variables. So S and R are the primary input variable. Apart from that, we have feedback variable. Now, one thing we must keep in mind, Q and Q bar are complement of each other. It means that Q bar is a just an inverted version of a Q. So we can list only Q variable rather than taking Q bar. Now, with that, we have three variables. So we are going to list the three variables. With that, we have 8 combinations to be accounted. So all the 8 combinations, the binary combinations we have written. Okay, fine. Now with these 8 combinations, one thing we can observe is that for a two rows, we have S equal to 0, R equal to 0. Two rows, we have S equal to 0, R equal to 1, and two rows, S equal to 1, R equal to 0, and two rows, S equal 1, R equal to 1. Now, S equal to 0, R equal to 0, as we have discussed in the last working mechanism, that it corresponds to the latch state or the memory state. So Q plus is same as a Q. So here 0 remains 0, 1 remains 1. Now with the S equal to 0, R equal to 1, it's a reset state irrespective of Q, Q plus is 0. With the S equal to 1, R equal to 0, irrespective of Q, Q plus is 1. So when S equal to R equal to 1, it's an invalid state irrespective of Q. Q and Q bar will trying to take the same value 0. So that invalid thing we are representing by X or a don't care in the output column. So the output here is the next state of Q, which is represented as Q plus. Fine. So the characteristic table is written by listing the input variable SRQ and the output Q plus. Okay, fine. So let's try to derive a characteristic equation from this characteristic table. So to do that, we require a K-map. So here's a K-map, and we need to draw this 8-cell K-map, and the 8 cells correspond to the 8 combinations. So we will label the rows with the variable S. So first row S bar, second S, and the columns R bar, Q bar. So R bar, Q, RQ, RQ bar. So the columns are labeled with the variable R and Q. So this K-map, we are going to simplify it for finding the expression for the output Q plus. Fine. We will number the K-map with the gray code. I mean the cells of the K-map with the gray code. Okay. Now, so we are going to fill in the K-map with the values under the column Q plus. So it is 0, 1, 0, 0, 1, 1, don't care, don't care. Now, with this, okay, uh, we have to apply the grouping of the K-map. So we can make a quad here and one pair here. So this corresponds to one term and this corresponds to the second term, right? There are two terms. So now the characteristic equation with that, the equation for the output Q plus will be, so the term corresponding to the quad, as it corresponds to the row, all the column variables being merged. So the column variable cancels. The Variable corresponding to the row is s, so it is s plus the term corresponding to the pair. So this pair corresponds to the column r bar q, and the two rows are being merged. The row variable cancels, so the term is r bar q. So this is the characteristic equation for our SR latch. Okay. Now let me come to the last part. So here is the truth table for this SR latch. You can see s equal to 0, r equal to 0 is the last state. It means the value of q and q plus are going to be the same, or you can say that the value of q is same as the last value. So if s equal to 0, r equal to 1, it's a reset, q will be 0. If s equal to 1, r equal to 0, it's a set state, q equal to 1. S equal to 1, r equal to 0, q will be 0. Not only that, here in the last column, you can see that the q bar, so with s equal to 1, r equal to 1, both will be 0. This is an invalid state. Invalid state. Right? For rest of the thing, q bar is complement of q. Right. So this is it about SR latch. Now here we have one important thing what we observed with s equal to 1, r equal to 1, it's leading to the invalid condition or invalid state wherein q and q bar are trying to take the same value. So this is this is a condition which should be avoided or which should be overcome. We will discuss about the solution for this in the next video. Thank you.